So additive manufacturing, it's a little bit of a different story compared to the ones we just heard about, but it's also aviation, and the title is How Will That and Will It Change the way we produce aircraft in the future? And is it just a hype or is it hype real? So the traditional manufacturing methods are hundreds of years old. So we have forging, we have smelting, casting, milling, drilling, forming, bending. All of these methods were used for hundreds of years already, and we know exactly what that means for the materials. We know exactly what kind of efficiencies we have, the density we know, the dislocations of defects we have, and we know exactly how we have to calculate these materials, and we know how to handle them. But they clearly have some disadvantages. One, of course, we have these many steps, they are rather expensive. So we have to go through all these different steps, one after the other. We have to do all the forging, we have to do all the material treatments before we can really use them. Once we prepared the single parts, we have to make complex assemblies out of them. So we have different single parts we have to assemble together, which takes time, which takes effort, skilled people for these complex processes. And we have a long waiting time, because from the raw material to the final product it takes a long time, and because we have these many different specialist activities in there, they're usually not happening in one place. So they are happening in different places, and if you're waiting for your final part, you have to wait for a long time to get it really in your hands. So the lead time is long, the storage has to be there, you have to store parts because they are ones of a kind, you have to store them in a warehouse, you have to ship them, you have to deliver them, so it takes a long time, especially in aviation, in commercial aviation, and Mike will support that. Time is really money there. And they're usually heavy because we have design constraints coming from the manufacturing, from the materials, and so we are really having heavy parts. And something magic happened in 1986. It was the year of the first patent for 3D printing. So there are different names for that. 3D printing is the most well-known name, but it's actually, technically it's not correct. So it's rapid prototyping at that time. Now it's called additive manufacturing, sometimes additive layer manufacturing, but even that is wrong. So additive manufacturing is a final turn, and what you see here, or what you saw here, is the Eiffel Tower printed with stereo lithography just in a couple of minutes. And that change happened in 1986 with the invention of 3D printing or additive manufacturing. And it's completely different because it's additive and not subtractive or formative like the traditional methods. It's bottom up, it's layer by layer. And you see here in this liquid, the liquid is then hardened with a laser beam, and the liquid becomes a solid structure, a polymeric structure, to really form parts like that. The challenge is, though, that this really has to be functional parts. So this is, especially in aviation, it's not just prototyping, it's just not a sample case like in this case where you just see a picture. It really has to be something completely usable in a predictive and reproductive way. And compare this with the traditional methods with experience of hundreds of years, it's really that we're at the crossroad of additive manufacturing, making this really something into a proven manufacturing process where you can rely on, where you have quality assurance, where you can make sure that the final part is then really strong enough for aviation use. And that is the challenge we are facing today. But the advantages we have are huge as well. So one is reduced weight. Because we do not have to follow the design constraints from traditional methods, we can apply bionics design, and I will give you some examples on that one. We can optimize a load path, and we can combine complex structures. We can reduce the lead time, as I said, with the lead time for the traditional methods. We can really reduce lead time. We don't need any shipping. We don't need no storage. We don't need no spare parts. You can really print spare parts on demand, on the spot, where you need that. Imagine an airplane flying somewhere, being grounded for technical reasons, and you print your spare part on the spot. And additionally, you can increase the customization because you don't have to have all the forming, casting parts. You can really print parts with a high value of customization. With more specific production, you can reduce the lot size to 1. You can really reduce the initial cost, and you can reduce the number of parts you need for the amortization. Some examples I would like to give you. We start with the topology optimization. This is the part which is passing around. This is the first step. Coming with a traditional load pass. It's a sheet metal bracket you see on the lower left side. This is a traditional part from an Airbus A350. And then with the topology optimization, we reduced the sheet metal to this topology optimization. But parts are just left away. So it's not really the perfect optimization. It's just leaving areas away which are not carrying any load. This is used on an A350 70 times per aircraft and is already in operational use. And you see the parts with this high value structure with the surface roughness, which is really good, which is passing around. The next step is then bionic design, according to experience you have from biology, because just following the load path you see with this part is sometimes not enough. In engineering, you have to invent new strategies how to optimize the structure. So it's not just leaving parts away, but sometimes it's the idea from biology to have a new complete layout of the support structure. So it's not something just traditionally thinking, but it's something you really have to start from scratch and copy something from biology. And this is just a mold, and we copied in engineering this way of working of the mold, how this expands this structure in nature. We copied that into an application in a partition wall of an aircraft, and we copied that into a computer model where a partition wall was built like that as well. And then with the computer model, we reduced again the structure out of that to find the optimal structure for this partition wall. So instead of just leaving parts away, we came from the mold solution, from the biology solution, with a new layout of the support structure carrying really the load. And you see that how the computer program was supporting that 3D process. So it's not only the 3D process, the printing process, the additive manufacturing process, which is important, but also the underlying CAD tools, the tools doing the stress analysis, doing all the calculations, which makes this really beneficial for the future. So it's a combination of Industry 4.0, manufacturing 4.0, with the digital data you have, with the computer models you have, with the computer optimization to really move ahead with additive manufacturing. The final product was then much, much better than the old one. The reduced weight from 65 kilograms to 35 kilograms, so minus 45% reduced weight. The displacement was optimized. Displacement was reduced by 10%. So with the attachment of the cabin attendant seat, we can really improve this partition wall. Of course, it's at the moment much more expensive, and a lot of work went into the different parts and to the connectors, because at the moment it's not possible to print such a big part. You really have to print smaller parts and you have to connect them somehow, and a lot of effort went into that. Then another sample case is a bionic lightweight design of a landing flap inspired by the water lily. Again, a new solution coming from biology. The traditional structure of a landing flap is with a lattice structure, so a rectangular structure, but with the idea from the water lily, a new landing flap design was invented where the load pass was coming in a similar way from the water lily. So again, the transfer from biology to design, and then with the 3D printing, with the additive manufacturing method, being able to really produce that in a new way, which was not possible beforehand with the traditional subtractive manufacturing methods. And then reducing parts. This is a sample case for a fuel connector for an A380, which consists of several different parts, and the manufacturing process is quite complex with the traditional parts. So we have 35 different steps there from water jet cutting, bending, milling, drilling, welding, of all these parts to really produce that single part which is in front of the rear pressure bulkhead of the A380. With the new 3D printed parts, we could really reduce 31 steps to 5 steps. So just laser melting, the heat treatment which you need afterwards, remove the support structure, the milling and the micro finishing, just 5 steps, and from 14 parts to 1 single part. So this is a huge advancement. A lot of lessons learned in this part. Of course, not easy to design the support structure. We at the beginning, we had some issues with the support structure bending. Of course, the heat treatment was quite complex, and we had buckling in the tube structure first. But with the new design of the support structure, we could really get rid of all these defects. And in the end, building in a complete airplane, is that possible? And yes, it is possible. We already did this. It's in the Guinness Book of Records. We printed a complete model plane, which was flying already 3 years ago, testing 3D printing. So it was not intended to develop the printing technology, but to really do rapid prototyping, to test out new concepts. And there we go along with all the different concepts we just heard about this morning with electric flying, because we can really try new configurations out with 3D printing, because we can print every 3 months, we can print a new model airplane and try new configurations out. And what is the future? The future is 4D printing. That's the next step. After 3D printing comes 4D printing. It's changing the configuration over time, programmable materials with kinematics, creating new structures and objects evolving over time. And just one sample case, this part consists of different materials, and if you put this in warm water, it changes the structure behavior. And this is a new future for us. After 3D comes 4D printing, and we can produce movable parts. And just imagine flap motors, flap gears, which you can just move around just with electricity or with heat treatment of different materials, and just get rid of gears and stuff like that, if you can really have changing configurations over time. In the end, you just have a simple box, but imagine that in the future for moving parts in airplanes, getting rid of that.